Okay, so what were we doing in the last class? What were we doing in the last class? आज क्या हुआ है? Why is the class absent? Very few students see it. Okay. आज सरप्राइज क्विज कर लें क्या? Yes. He's so happy. Yes, sir. आज ही कर लेते हैं. Okay. So what were we doing in the last class? Cache subsystems. Okay. Why do we need these caches in the first place? Faster memory closer to the chip. We need a faster memory closer to the chip. Why? And to operate with the same frequency as the processor. Okay. So our process. So we needed. Okay. So थोड़ा सा और पीछे जाना पड़ेगा इसके लिए. What we had discussed was that logic becomes faster with every technology. Now it means that your processors and your data path will be faster with every technology. However, memories do not scale in performance in the same way as logic scales. And we had discussed multiple reasons for that. We had discussed reasons like that the memory cell is not CMOS. There are so many figures of merit that need to be optimized, stabilized. We have sense amplifiers, which are analog in nature. Their offset requirement would probably increase with technology scaling instead of reducing with technology scaling. We talked about aspects like RC of word lines being increasing, RC of bit lines also increasing. So with all these things coming into picture, memory performance can't scale. Now, if the memory performance doesn't scale, but the processor becomes faster, what happens? Your processor will send an instruction to the memory and then has to wait. We call this as stalling, where the processor is ready to work more, but is in a situation where it can't. So it has stalled. And to avoid stalling, that is to improve overall user experience, to improve overall throughput, we need to have faster memories placed closer to the processor, which can respond to the processor requests at the same speed that the processor is operating it at. Therefore, the same frequency requirement for L1 caches and processors. That L1 caches have to operate at the same frequency as the processor. What about L2 cache? Does it also need to operate at the same frequency? No. Why? Why no? Because we focus processor and directly in time L1 cache. So the data is required. So we talk about locality of reference. So most of the data goes and that's required at that point of time. Will be there in the L1 cache and then so L2 cache need not operate at the same frequency as the L1 cache. And the reason behind that is that there is a locality of reference. There is a property of inclusion that we talked about, that whatever you need in L1 cache is also already available in L2 cache and L3 cache, whatever. But more importantly, because of locality of a reference, most of the times, whatever data you need should be available in L1 cache. Now, whenever a miss happens on the L1 cache, only then L2 cache would be accessed. The probability of stalling is reduced. And that's good enough for us. Because for a very large memory, if we try to improve its performance, we would have to give a lot of area, we will have to give a lot of power. So for the L2 cache, we said, okay, let it be high density. L2 cache can be slower, but L1 cache has to operate at the frequency of the processor. Are you with me? So this is essentially a PPA trade-off only, where you say, I want performance. This big memory, if I try to get the kind of performance I need, I will have to give it much more area. Not affordable for us. So what we do, we say, okay, only a small memory operates at the speed of the processor. So those of you who are doing the creativity course, this could also be considered as utilizing the principle of segmentation. कि आपने एक बड़ी मेमोरी को छोटी मेमोरी में डाल दिया. The inclusion property can be considered as the principle of nested dolls, where whatever is there in the first one is also available in the next levels of hierarchy. So I'm just connecting the dots for you so that you are able to relate that देखो ये सब चीजें हम वहां भी कर रहे हैं, यहाँ भी कर रहे हैं. All these things are, so whatever is there is not theory and whatever is there is not magic. These are principles which are well established and they are being implemented in memories also. Okay. So we talked about key properties of caches. First one we said was the locality of reference. That we know that whatever program I'm trying to load, my next access or my next memory access or request would be around the same program only. So when I bring something from the L2 cache or from the L3 cache or from the main memory, I bring in a large chunk of data. What is this called? This large chunk of data that I bring in one go? A block. We also use the term line length for it. How many words will I bring? But a block would have a large number of words, not just one word, because my present request was for only one word. But I know that because of locality of reference, I can bring a larger chunk so that my next accesses don't result in a miss. And at that point of time, we had also discussed about the impact of line length on miss rate and overall access time. What happens? What is the impact? How do we see that?
The access time increases because of the larger block, but so the P miss, the probability of missing will reduce. But along with that, the access time will also.
Will it reduce monotonically? No. So the probability of miss will initially reduce. If my line length was only 1, now exactly because of the locality of reference, after the first miss, I'm expecting a second miss and a third miss and a fourth miss. Are you able to see this? But since my line length is larger than 1 and as it increases, because of that locality of reference principle, my miss rate reduces. But then why does it not continue to reduce? Why does it start to rise again?
Because when we go to large block size, there is good spatial locality within one program, but we cannot accommodate more larger blocks.
Yes, because today's system. So if we were to talk about a system which was there, let us say in 1980s, early 1980s, first rudimentary computers, they would do only one task at a time. Only one thing you could run on them at a time. One calculation is happening. But today's systems multitask. Today's systems run a lot of programs in parallel. There is an operating system which handles prioritization for those systems, those programs. So you will need to bring different kind of programs into the processor at a higher priority every now and then, and they will have their requests for data every now and then. It means that multiple different kind of data needs to be stored in the caches. However, if the block size is very large, then suppose my memory has 256 words and my block size is 32. How many different kinds of data can I store? Quickly. 256 words, 32 words ka line length hai. How many different lines can I store? Only 8 lines. All of you have done Control-Alt-Del on your computers? You have never done Control-Alt-Del on your computers? Task Manager kabhi nahi dekha kisi ne? All of you have seen the Task Manager? How many tasks do you see running at any point of time? If no program is running, you're not even open, you just logged in into the system. How many tasks do you see running even at the login stage? 30, 40, 50, more than 50, whatever. Now you start to work on it. 2 days you have not reset your computer. How many tasks could be running? Hundreds of them. Not all are active, but of those hundreds of them, Definitely 10, 20, 30 will be active. There is a task of clock, there is a task of this, that. So many tasks have to happen in the processor. But you have only 8 blocks. So misses start to happen. As the line length increases, because of limited capacity of your L1 cache, the number of misses increase. As a consequence, your effective access time degrades. There is a sweet spot. Are you able to see this? Any questions?
So to reduce the spatial conflicts, we should not just abruptly increase the block size, but instead we can increase the cache size.
But if you increase the cache size only, what happens? The intrinsic performance of the memory degrades. Because a 1K cross 32 memory is much faster than 2K cross 32 memory by the virtue of smaller RC there. Are you able to see this? So not only memory design in itself handles a different kind of complexity, memory subsystems also have reasonable complexity in them. In terms of subsystems, in the last class, we also talked about the controller and the coprocessor that you need to have with the DRAMs, or the controller that you need to have in the memory subsystem. So why do we need these controllers and coprocessors?
The CPU can wait for interrupts.
To offload some tasks so that the CPU can focus on what we wanted to do. But which tasks are these? Why do we need a see? I need to offload something. It is becoming so cumbersome that it is impacting my other performance. So these coherence management is a fairly complex activity. You do not want the microcontroller or the microprocessor to focus on this. It's a fairly complex activity, but I know what, the algorithm is fixed. It is not कि एक बार कुछ और करना होगा, एक बार कुछ और करना होगा. It's not like I can one time run a Word program, then at another time a C program and something like that. So because my loop of activities, my algorithm is fairly established, therefore a coprocessor which does just that, a very small light one, I need to put for the DRAM access. A small controller I need to put for the memory subsystem control. And as I was mentioning in the last class also, there are numerous job opportunities in this domain, which people are not able to fill because some of them do not know computer architectures, others do not know memory design, and then they struggle. Are you able to see this aspect? So we also talked about one more thing that we do to reduce miss rate. We talked about direct map caches and fully associative, and we talked about that over there. What was that? We talked about another feature or a parameter of a cache subsystem, which we said helps us to reduce miss rate.
Associativity.
That was associativity. What is associativity?
Any location of cache.
So we talked about two extremes. We talked about an extreme which is fully associative, the bottom one over here, where we said that fully associative memory, any data can go anywhere. So when you want to match the tag, you will need to match the tag of incoming request with every location inside the memory. Now you are doing everything for speed. So all those comparisons have to be done very, very quickly. They can't be done sequentially. They have to be done in parallel. So it requires a huge amount of power consumption. The other extreme was direct mapped. Oh, I will just look at the LSBs, and whatever were the LSBs, I will put it there only. And then we said there is some intermediate game that we could play, where we said that we have 4 locations in a given set where a given set of LSB address can be sent, not just one. So I have 4 sets or 2 locations. So I have 2 sets. As soon as I do that, now what happens? Now, when my data comes, there are 2 different applications using data from same LSBs, they still have four different places or four different choices to put the contents inside the L1 cache, L2 cache, wherever. So I do not need to replace current data very frequently. As a consequence, my miss rate reduces. It's a neat compromise between a direct map, which is definitely very low power, no comparison needed, just LSBs देखा और आगे भेज दिया, or fully associative, a lot of power because my data could be anywhere and I have to compare every tag. Set associative means only the number of sets that I have, only that many tags I need to compare. That I can do in parallel. Yeah.
It would also be very high in fully associative because we need more comparative.
Yeah. See, when you need that performance area, you can still think of giving, but the power is what is prohibitive. So you still use fully associative caches. These are called tightly coupled memories. And those of you who will go into GPU teams or who will go into uh, uh, these processors with Qualcomm and others, they use tightly coupled memories in their mobile application processors. Okay? GPUs, NVIDIA GPUs use tightly coupled memories. Apple neural chips also use tightly. So tightly coupled memories are fully associative, but they then are kept very, very small. Very, very small. Just 128 words. That's sufficient for them. Is that okay? Yes, you may say so. Associativity depends on what is my requirement. I may have two set associative if I know that's a very light processor and I will not have multiple different kinds of tasks running in parallel. For example, edge processor for a sensor. इसमें बस ये देखना है whether this value is greater or lesser than something, and if it is greater than उसको उस data को कहीं भेजना है. Let us say. Now there are just two things. One activity it is doing is comparison. The other activity is doing is the communication protocol. So I don't know. I know it's not a general purpose processor. It's not a processor that I'm going to load in a hugely big way. And just two ways could be sufficient, or even a direct map cache could be sufficient. But when you're talking about very high performance processors, they just say tightly coupled, fully associative map caches are used. In supercomputers, again, depending on what is the requirement, you may have some tightly coupled memories and then set associativity. L2 could be set associative. We could see, I don't know. So all those things are possible. That depends on what is the performance requirement of your system. Are you with me? So associativity, as we say over here, is about which all locations my particular word could be placed. Is there only one location, which is the case in direct map, or in multiple locations, 4 places, 2 places, 8 places? That is the size. That is the size of your associativity. Or is it fully associative anywhere inside the map?
Could we sometimes also said that there is, when we talk about replacing particular blocks, so could we also say that sometimes like there are programs also which have a priority order? So
Yes.
in those cases, that would also have to be considered, right? When we
Oh yes, that is what the operating system does. That is why I said that you have to, if you really want to have a complete understanding of computer engineering, you should do courses on computer architecture, you should do courses on operating system. They are two very, very critical courses that every computer engineer should know. You think you are EV, but computer engineering is EV. कंप्यूटर साइंस सॉफ्टवेयर की बात नहीं कर रहा, मैं कंप्यूटर डिजाइन की बात कर रहा हूँ, आर्किटेक्चर डिजाइन की बात कर रहा हूँ. ऑल दीज कंपनीज they need computer engineers, and then you should do those courses of operating systems and computer architecture to round up your understanding of the topic. That is the reason why these are also elective courses for you, but not for ECE track. Are you getting it? Because computer engineering is a very fair specialization that EV students can target. Okay, so associativity, fully associative, direct mapped, and set associative. And set associative, ये उसी चीज को we are just talking about in terms of where could you place. All of you have watched the video by now, am I right? Anyone who has not watched? You not watched the video for cache subsystems? Why? So this is again, the blue bars represent that where could this particular data go to. And fully associative, it could go anywhere. In direct map, it would go to only one place. In set associative, it could go to multiple locations. Is that okay? And this is again direct map का example कि ये यहीं जा सकते हैं और कहीं नहीं जा सकते. So this is the lower one is the real main memory or the L2 cache, and then the top one is the smaller memory or the L1 cache. There could be multiple locations in L2 cache, but still just one location in L1 cache. Okay. So contents of a cache block, we already said there would be data, and then there could be byte select, cache index, and cache tag. Byte select and cache index are just about how to go to the exact byte. So my word could still be much longer. I could have a 64-bit word. Now, which of those bytes do I need to give to the processor? Okay. So this is, I would say, when you're talking about 8-bit processors, this is valid information. But today, almost the entire thing is 32-bit or 64-bit. So byte index kuch khas hai nahi. You need the entire 64 bits in one go. Okay. But when you are working with 8-bit processors, because you would, these co-processors for DRAMs could be small. So you may need to use that all this, but practically, अगर आप main processor पे काम कर रहे हो, तो byte index may not be something that should worry you. But tag is something that we need to understand very, very well. Tag is all the other bits of the address which are not used for identifying which bit or byte I need to read.
Can you give an example of an application where you would need only specific bits out of the 8 bits?
Bit nahi hoga, byte hoga usually. But for example, if you have a very simple microcontroller, 8-bit microcontroller, but your memory bus width is large, because it is an 8-bit microcontroller, you only need 8 bits at a time. The processor would only request for 8 bits. It cannot request for 64 bits. You are fetching 64 bits because your line length is, let us say, 8. So you're getting 8 words in one go, but you still need only 1 byte to be sent to the processor at a time.
So this is like a strobe signal.
Not strobe signal. Strobe signal just comes and goes. This is address. I need 5th byte of that particular line to be sent to me.
Strobe is also multi-bit signal.
So what I understand about, so probably यहाँ पे language का mismatch है. What I understand with the strobe is you give a small strobe and say that, okay, I need new data. So आप अगर वही कह रहे हो, address ही कह रहे हो, तो I'm just clarifying that what we mean over here with byte select is, or word select in a given long line is, which word do I need to get to the processor from this one line that I have fetched. Is that okay? So anything that is beyond the addressing requirements of the processor, addressing requirements of your cache and the processor is what we call as tag. Is that okay? Yeah. You had a question.
So tag and index and how it is used in our different setups.
So I would say आप उसको इतना मत देखो. These are all जितना भी आपके addressing के बाद का हो गया, that is all tag for you. If index is used for addressing, then that is not tag. Whatever else is tag. That is why I'm bringing you the a more generic understanding of this. All index hai, byte select hai, all of that is only about identifying which address to be picked up. Nothing else. Tag is what you will need to match. Okay, everything else is simply addressing. Okay, we did talk about this, that if your line length is, if you have a direct map cache, or if your line length is small in such a way that एक डेटा मांगा, दूसरा डेटा सेम एड्रेस को मांग रहा है, then you will just keep on playing between misses. That's a ping pong effect that impacts the performance of your system terribly bad. Okay. So all of this we have already discussed in one form or another in the previous class itself. So that's there. This is about the fully associative cache where all the cache tags have to be compared in parallel, which is why it is also very high power consuming. Okay. This is about the two-way set associative where we say that, okay, cache tag aayega, a valid bit aayega aapke paas. If the bit is valid, then you compare the cache tag with the tag that you got from the processor. If it matches that particular set data, you go and send forward. Otherwise, you go back to the L2 cache and fetch new data. So all this we've discussed, so I'm moving a little fast.
Have a cache tag, like one tag have a special cache. So for a particular address, we will have tag and index. So if there are two different blocks at which same tag and same index come, how we will identify which are with it?
So you are saying that same address is placed in both the two sets. That is what it means. Because everything else is matching. So it is placed in both the sets. So first thing, why would you do that? Why would the operating system do that?
Select which set we should put it.
Yeah, that is a different thing. But the situation that you said that, okay, same data, same tag and everything is there in two different sets, that is hypothetical. That your operating system will not allow. What will your operating system allow? What your operating system will ensure that if there is a data which has an invalid bit, tag match, but the bit was invalid, I would update the contents and also update the valid bit. That operating system may do. But putting it in two different sets is not what a cache, not what an operating system will allow or the memory controller will allow. Okay. Now we come to how would you replace? That was what your question was. So there are multiple policies through which you could replace. You could say that I will replace the least recently used. Someone would say, oh, jo last aaya tha, usi ko replace kar do because, I'm watching a movie. I've already watched that frame. I don't need to watch that frame again. So replace the most recently one because that frame is already gone. Or random. बिल्कुल random. किसी को भी हटा दो. And you will see that if my cache size is large, random and LRU are almost the same. Are you able to see this? If my cache size is small, then there is some difference between the two. Otherwise, random is as good as least recently used or most recently used. You will see it could be. So if you have sufficient area, sufficient resources at your disposal, then all this is meaningless. Only in very constrained systems, like when you're doing edge computing, where you are truly constrained about how much memory can you put, you will need to think about those aspects. And then there, the performance would actually, or the choice of algorithm should depend on what is this constrained system required for. See, एक चीज का ध्यान रखो आप लोग. The age of commodity products is such that जो बहुत जेनरिक आर्किटेक्चर्स या बहुत जेनरिक पॉलिसीज होंगी ना, ये हर कोई कर लेगा. ठीक है, हर कोई कर लेगा का मतलब ये है कुछ टाइम बाद एआई भी उसको कर लेगा. और या ये कह लो कि एक बहुत यंग इंजीनियर के सपोर्ट से या एक बहुत यंग इंजीनियर एआई के सपोर्ट से कर लेगा. अब आप हर समय तो फ्रेशर्स नहीं रहने वाले. 4 साल बाद 5 साल बाद आपकी सैलरीज बढ़ जाएंगी. काम अगर आप यही करते रहोगे जो एक यंग इंजीनियर की तरह कर रहे थे, तो you become a liability for the organization. So you will see that, and this is not just for you. This is also equally true for companies themselves. If they have a very generic offering, any other Tom, Dick and Harry startup will also get that generic offering on the table. There are these C2S schemes. There are so many things which enable people to work on the generic offerings. Startups can get funds and they can displace you. They can do something which is simply path breaking, and they can replace you. So for companies also, they also look at ways in which they can specialize. So they look at opportunities to customize design. This is not full custom, but customized. So different aspects of product development life cycle, like those that we discuss in the IPDCP program at CIPD, those become very relevant, where we start to talk about what is the user need. What is it that the user needs? How can I minimally meet that requirement with minimal investment in my resources, meet that requirement? And when I know that, then I can have a very well optimized system for one particular application. So I was talking to Professor Dhananjay Gadre from NSUT. He comes and teaches in the IPDCP program. And he said, Anuj, yaar, let us make a small microcontroller. मैंने कहा ओके. कहता है पता है चाइना ने क्या करा? क्या करा? तो उन्होंने कहा कि चाइना ने देखा कि जो यू हैव सीन दोस रोड साइड छोटे छोटे नगेट्स लगे होते हैं एलईडीज जिसमें ब्लिंक करते हैं, ऊपर सोलर पैनल भी होता है. He said China saw that this is a huge market. Many countries would need these small things. And what does this controller do? Nothing. सोलर छोटा सा पैनल लगा हुआ है जो उसकी पावर आ रही है उसको एक बैटरी में स्टोर कर रहा है. एंड उसके बेसिस जब जो ही देख रहा है कि वो बैटरी के अंदर जो इनकमिंग करंट है कम हो गया, इन एलईडीज को जलाना शुरू कर देता है, वो भी एक पैटर्न में, राउंड रॉबिन में. Is it too complex? No. I just need an 8-bit microcontroller, a very, very light microcontroller to do it. And China made that chip in 2 or 3 cents. Now, how did it make it in 2 or 3 cents? Because उसने कहा कि मेरा तो बस यही एक application है, just one application. And today, everywhere in the world, it is only that Chinese chip that goes. And even at that 2 to 3 cents of pricing, it is making profits because of the volumes. So you will realize that when you specialize for one particular activity and super optimize just for that, and make big profits. You could also do it the other way around. For example, you could say that I want to specialize only for cloud infrastructure, huge GPUs. Okay. Now the need is such that you need those GPUs to have a particular kind of performance. So you're specializing to get the performance there. Every 10% improvement in performance, the price of or the pricing of your product could be raised. The margins that you are getting can be raised by 20%. That's a premium market. So there are both places. I'm giving you both the plays. One is a cost play, the other is a performance play. Because you can optimize for both. But optimization for specific use cases leads you to much higher profits. That is the only way big companies, not China companies, survive the onslaught of China. Where they say, no, we are not entering the commodity market. Not just China, Korea, all of them. They just go into a huge scale and make anything commodity. So they say, oh, let us specialize. I'm telling this to you also because when you think of startups yourself, and you should think, see, Anshuman was here and he shared about what kind of opportunities our ecosystem offers today. Whether you think of a product startup in terms of an embedded system product, or you think of a product startup in terms of an SoC product, whatever you think of, you should think of it in those lines. You are see, at IIIT, we have a very, very, very vibrant entrepreneurship ecosystem. Huge number of courses that you can take to gain those concepts, to get that knowledge, which can help you be an entrepreneur. If you are from any other college, even IIT Delhi mein bhi itna vibrant ecosystem nahi hai. They have many more departments than IIIT Delhi. But if you count the number of courses or the percentage of courses that we offer on entrepreneurship over here, You don't see anywhere else. So आप बहुत uniquely placed हो to even do deep tech startups, not just service startups, deep tech startups के लिए. And if you are interested, I'm giving you these tips कि आप कहाँ सोच सकते हो. Because generic commodity में जाओगे, you will always lag behind. Someone will always be more efficient than you. As startups, you can't exceed the efficiencies that these big companies can bring in. You should look at what to customize, where to specialize, and make a unique offering. Even commodity is fine. जो China ने करा 3 cents का microcontroller, it made it a commodity. But so specialized commodity की price को बिल्कुल squeeze कर दिया, and still making profits with that. So be aware of these things, and that is where I'm saying that even if you are not constrained about resources, either of these two algorithms are fine. But when you are constrained about resources, you have to design your operating system, your replacement policies, everything extremely carefully. In fact, in such a 2 cents microcontroller, you will not have an operating system at all. All this will be hardwired. Are you able to see this? Because you don't need nothing.
Are these like the only two options? Because if you
No. I just showed two. When you do an operating systems course, you will see there is a wide range of options. There are weighted replacement options. There are first in, first out. वही मैंने कहा most recently used. FIFO is most recently used, or LIFO, जो भी. So all those things could be there. Multiple ways operating system could see. What I am showing is random is as good as any one of them if there is no constraint on resources.
So in hardware, how can you implement something that is random? What do you mean by this? If you have to have some kind of
So he's asking, how do you implement something like random in hardware? It could be anyways. For example, there are these physically unclonable functions which generate a random signature, but that random signature is constant. So such physically unclonable functions are random but fixed and are also used for security purposes. Okay, you could have random number generators which could be based on the clock time. Another random number generator could be based on a mix of clock and location, or clock and the number of processes running. So random number generators hote hain and you use them to generate something random. Okay. Okay. Anything else? So we also talked about write. In the last class, we said that write could happen in 2 ways. One is write through. Whatever I'm updating in the L1 cache will be updated in all the other hierarchy. Because of the inclusion property, everyone has that same data. Or I could be doing write back, where I will not update the higher hierarchy. I will simply put the valid bit as 1 or 0. Thus saying that the data in the higher level is invalid now. And I will do the write only at the closure of the program. Again, this is a algorithm, or this is a policy that you will implement in your operating system based on the kind of application that you are running. But a cache subsystem has to allow both of them. Yeah. People use the terms interchangeably, dirty bit, valid bit. It's the same thing. So, write, because when you're writing back to the L2 cache or L3 cache or the main memory, those will be slow. So if you do need to do a write through, then what you may need is, you may need a small buffer. Suppose your L1 cache is 1 access per cycle, but L2 cache is 8. So you may say, okay, let me have a buffer of 8. Or let me have a buffer of 20. So that if there are multiple write back requests or write through requests, I don't need to stall my processor. And again, there is an optimization over here. This is just like आपके दो particular blocks हैं जो अलग-अलग frequency पे operate कर रहे हैं. and you have to interface them, then you need to put a small buffer in between two FIFOs, and those you have to put. How to size that? It's not कि हाँ भाई इतना रख दो. It's again based on some assumptions that you will see based on what program you are running, what is the architecture, and all those things. So these are topics linked to computer architecture. Uh, there are again many algorithms to help you arrive at those. What I'm pointing out over here is that between L1 cache and L2 cache also, just for the right operation, you may need to put a small buffer. This buffer could be is like a FIFO. Is that okay? So with this, we kind of close the topic of caches and we move on to the next phase, next chapter of this course, which is DRAM design. So DRAMs we have discussed early on when we were introducing this course. So what are DRAMs?
Dynamic random access memory.
DRAM stands for Dynamic Random Access Memory, full form. Huh? So what is the key difference between a DRAM and an SRAM? DRAMs store data on a floating capacitor. SRAMs also store data on some capacitor. That capacitor you do not see. It's not shown in the 60 memory cell, but it is also some charge storage mechanism. You're storing some charge on int and int bar, q and q bar, whichever name you want to put it. But you're storing some charge somewhere. So if you're storing some charge, there is bound to be some capacitor that we are talking about. So DRAMs also stored some charge on a capacitor only. But this capacitor is a floating capacitor. In SRAMs, because of this latch, the inverters there continuously establish the same charge at the capacitor which needs to be charged or needs to be discharged. In a DRAM, there is nothing that can reinforce the charge on the capacitor. So since there is nothing internal to the memory cell that can do that, DRAMs require a refresh, where you access the memory cell, sense what is inside the memory cell, and write that back. So any leakage that might have happened into or out of the memory cell, you kind of take care of that. So if refresh has to happen because of leakage, then when? If refresh has to happen because of leakage, then at what temperature or at what PVT would you need more refresh? चलो डीवीडी क्लियर हो गया at least. So leakage is higher at higher temperatures. We know this. So if the temperature of my DRAM increases, I will need refresh more frequently. If the VT of my pass gate is reduced because of whatever reason, whether it is a fast slot or I'm running on forward body bias, whatever, I wanted speed, I put forward body bias. Whatever it is, if the leakage of the pass gate is larger, I will need faster refresh rate. Now, what is the problem with refresh rate? Why am I so worried about refresh rate?
This is the time that you cannot use for your normal.
See, what does refresh require? Refresh requires that I should read that particular location and then write back the data. It means that my read circuit is also busy and my write circuit is also busy. Are you with me? So actually DRAM में read write circuit same ही होता है. But what I am saying is that my memory array is busy. If it is busy with some internal operation, can I have an external access come? No. So refresh is a period of non-availability of the DRAM for the system. The more your refresh requirements, the more the non-availability of the system there. So the processor has to stall. The processor has to wait. And that is where, and then obviously, these are just maintenance operations, but they require read and write inside the memory. So that is extra power. So power bhi hai, but also non-availability. So the system starts to stall. And because of all these different reasons, so we will go further and we will see that okay, DRAMs are so slow, and you need to speed them up through different access protocols. You have DDR1, 2, 3, 4, 5, and all those things. So it's a fairly complex process to handle access through DRAMs. And just because of that, you have a coprocessor associated with DRAM access. तो आपके DRAM chip के अंदर ही coprocessor होता है, एक छोटा सा processor हो जाता है, which ensures that all these things are taken care of. All the protocols, everything is handled well. Okay, but refresh is a issue because अगर आपको refresh जल्दी जल्दी करना पड़ रहा है तो आपकी memory unavailable हो रही है. तो अभी हमने देखा कि refresh is dependent on temperature. If the temperature is high, leakage is higher, so I need higher refresh. What can I do to avoid this? I can increase the size of the capacitor. But if I increase the size of the capacitor, what will happen? Area may increase. May increase. अभी हम may की बात करते हैं, ठीक है? The speed may be slower. Maybe. अभी हमें पता तो नहीं. Maybe. But what we definitely understand is that something needs to be given at the memory cell level. You are going from an SRAM to a DRAM to gain density. If you need to use a big capacitor, something got to give. So the main reason why you were switching from a SRAM to a DRAM, that is getting eroded in some way. And that is where when it comes to scaling or scalability, DRAMs are not very scalable. Because this capacitor needs to be large enough. अगर capacitor बहुत छोटा हो गया, तो very little leakage. See, leakage is increasing with every technology. So you need to keep on increasing the capacitor size. So that is counterintuitive to scaling. Also, the kind of doping and the kind of critical charge that you will require with a smaller capacitor, that starts to become challenging. And therefore, the capacitor size cannot be reduced to very small value. So capacitor cannot be scaled. That is becoming a challenge. So scaling, you will realize, so we saw in SRAMs, scaling is an issue. When you are starting with DRAMs, I'm telling you again, scaling is an issue. We will go to flash, I will tell you again, scaling is an issue. And that is the reason why there is a very strong push for emerging memories which are not storing data on the basis of charge. SRAMs, DRAMs, flash, all of them are charge-based memories. But the new emerging technologies that we are talking about, for example, RRAMs or MRAMs or PCM, they're all resistance-based methodologies. They toggle the resistance of the memory cell. So the current changes. You measure the change in current then. And that is why there is a huge effort to somehow move to resistance-based memories. They appear to be offering more scalability prospects. Okay? So how do you write into a memory cell? You take the bit line to the level that you want to take it to, and you take the word line high. Have you noticed one thing over here? I took the bit line only this much down, but the word line I took this much up. What is happening? Sorry?
M1 will be faster, it is getting more gates of and the charge being stored.
So because leakage is a very, very critical issue with DRAMs, what you also could do is you will use a very high VT device for the pass gate. Or you could use a thick gate oxide device for the pass gate. So that leakage is not there. But as soon as you go to that kind of a VT or that kind of a gate oxide, you need higher voltages to turn those devices on. So the word line is boosted, is driven to a higher level than regular VDD. तो चार्ज फॉर्म की हमने एक नेगेटिव बिट लाइन के समय बात करी थी. Variants of those charge forms will be used in the DRAM also to boost the word line. Are you able to see this? So you will notice that बहुत छोटे छोटे nuances हैं which you need to understand so that you can know the topic well. Okay. How do you do the read operation? Again, you take the word line high, and then that once the pass gate turns on, it will couple its charge onto the bit line. And the bit line will go to 0 or to 1. And when that happens, do you also realize that I am continuing to write the same data back into the memory cell? So unlike SRAMs, where when I turned on the sense amplifier, I would disconnect the bit line from the sense amplifier. That was what we did in the SRAMs. In DRAMs, I cannot afford to do that because I have to write back the data into the memory cell. So as soon as I do charge sharing between the memory cell and the bit line, both memory cell and bit line will be at VDD minus X. If I had stored a 0, it will be at VDD minus X now. If I had stored a 1, there will be no change. But if I had stored a 0, it will be VDD minus X. Both. But you wanted to store back a 0 now. So what do? As you read, you also write back. So the word line continues to remain on until the read operation finishes. And whatever is the charge on the bit line at the end of the read operation, that charge is also stored on the capacitor. So to refresh, what do you need to do? You just need to read the entire memory one by one. Every row you read one by one. The contents will be refreshed. That is what regular read operation does. It reads and writes back. That is what you wanted to do with the refresh. So you just read the entire memory and it gets refreshed. But through the entire read process, now your memory is not available for the system. Are you able to see this? See, SRAMs ke andar, when you have to do read and write, or this is called as read modified write, then you first do a full read operation, you turn out the sense amplifier, then you do a full write operation because write driver is needed. In DRAMs, read modified write is the default read. Are you able to see this? Read and write both happen in every read cycle. In SRAMs, you only read. Write driver is not even activated in the read cycle. When you need that functionality, you need a custom memory which would read and then write back the data into the memory. But over here, you don't need to do that. This is the part of the read process itself. That's how it is designed. Okay. So we just talked about refresh and the kind of numericals around refresh. We could talk about the leakage went this much time. This is the excess time. So what is the non-availability? Okay. So इस तरह के numericals आ सकते हैं. You should try and you should just work it out for yourself. Is that okay? How many of you have seen the DRAM lectures? मैंने पिछली क्लास में कहा था कि पढ़ के आना. See, I am taking a lot of extra time to teach lots of new topics to you which are not there neither in those lectures nor in the slides. And to get that time, to be able to tell you those things, I need more time in the class. To get that extra time in the class, I need you to be prepared with what is already available to you. If I have to repeat everything that I have already shared in the videos, I will not have time to tell you new things. It entirely is your choice. This is an elective course. This is not डीवीडी में आप कहते कि नहीं आप हमें पढ़ने को क्यों कह रहे हो? चलो ठीक है, आप बच्चे हो, छोटे छोटे बच्चे हो, आप काम नहीं करके आओगे, आपको स्पून फीडिंग करना है, आप मांग रहे हो. This is an elective course, advanced course. I will not want to lower the level of an advanced course just because you people are not preparing yourself well. If you've taken a course, do it the way it should be done. नहीं तो मत करो. Are you with me? And ऐसा तो नहीं है कि this was your first course or you're forced to take this course. You already taken one course earlier with me. You know that I insist that you have to watch the lectures before you come to the class. So this is not new news to you. So you knew what is the burden that you are taking up when you are signing up for this course. So this is not fair to me. Because I know that after some time you will say, sir, job nahi lag rahi, please help kar do, yahan kar do, wahan kar do. But then you are not doing your job now. Okay, so DRAM, we understand the entire functionality is based on the capacitor. Are you with me? सब कुछ हम उस कैपेसिटर पे स्टोर कर रहे हैं, उस कैपेसिटर के साइज को हम बड़ा करना चाहते हैं, उस कैपेसिटर की लीकेज को जीरो करना चाहते हैं. So many things are dependent only on the capacitor. And therefore, there's a lot of innovation that has gone into designing these DRAM capacitors. This part of the chapter is majorly historical. Okay. And none of this I am going to ask you, but it is important for you to understand how much jugglery has gone into arriving at DRAM capacitors or kinds of capacitors that we today use on the SOCs, so that whether it is a ADC or a DAC or anywhere you need a capacitor, the same technology can be used. It is made available and it can be handy. So over here, do you see where is the capacitor? Look at this. This is the poly plate, one side of the capacitor. The black one over here is the dielectric, and this is the storage. The pink one is the other plate of the capacitor. And this is how, so this is just one thing, and over here you see we've tried to make multiple fins so that in the same area, XY area, I'm using multiple fins in the third dimension. So again, those who are doing the creativity course, new dimensions will appear, add dimensions. That is a creativity principle. So you are seeing that this is already applied in the vertical dimension over here. अभी तक हम जितने भी structures देख रहे थे, हमने जब भी transistors देखे, we always talked about planar. But you see, third dimension was already appearing. This is long back, 1980s. FinFET तो अभी आया ना, 2010s में. But third dimension in ICs was already there long back in one device itself. Anyways, it was there. You were adding multiple metal layers, but this was also there. Okay. This is how it looks like. There's a bit line. There is this one particular side of the poly, and then the other plate of the poly. And that's where your capacitor is. Stacked capacitors were put where the capacitor would be put inside, poly 4 capacitor plate, for example. Again, this is a capacitor over bit line. So bit line hai, uske upar higher levels pe jaake you're making these capacitors. These were, I would say, the first kinds of, so ye to poly capacitor hai, But इसी तरह से today we have metal and metal capacitors, MEM capacitors or MOM capacitors, which are designed on the top layer. Between metal 5 and metal 6, you will have a capacitor. Where again, there is extra metal layer and a very thin dielectric and another metal put. So these capacitors are made on the device vertically. What that means is, capacitor को बनाने के लिए आपको area नहीं देना होगा. See, we started DVD with the capacitor. Which capacitor was that? MOS capacitor. याद है? We started DVD with the MOS capacitor. So you always had a capacitor on our devices. As soon as we came to the MOS technology, we had capacitors already inbuilt there. But putting a MOS capacitor inside, so अभी हमने जो DRAM के अंदर capacitor देखा, if you try to put a MOS capacitor, that's a full device in itself. That will take a lot of area. So now we are looking at how to have denser capacitors than the MOS capacitors. MOS capacitor तो हमेशा से था और है, आज भी है. आप जो हमने राइट ड्राइवर की बात करी, we talked about a MOS capacitor there, did we not? But over here, we cannot be putting MOSFETs everywhere because the area gain that we targeted would be lost. So now we are somehow trying to get that area gain with other kinds of capacitors, and we are going into higher layers or fractals. पता है आपको? How many of you have heard the term fractals? Fractals. Just 2-3 people in the class? Not done a course on computer vision? None of you? Okay. So you've seen a snowflake? How many of you have seen snow? Many of you have seen. So if you start to observe a snowflake under a microscope, now I know none of you have done that. I'm telling you this, okay? And you can find out online. When you start to observe a snowflake under a microscope, you will see that it is exactly the same structure that gets repeated over and over and over again at different levels of zoom. That is what is called as fractals. That you have the same structure at the bottommost thing, which would repeat, and you will create the bigger thing. Look at it also as, अगर हम थोड़ा सा atomic structure की तरह से देखें, तो the way we understood the atomic structure was there is a nucleus and there are electrons moving around it. That was one level. Then you look at the solar structure, there is the sun, there are planets moving around it. You look at the Milky Way galaxy, there is a center, then there are stars moving around it. So one could say that this is a fractal. So in nature, numerous things exist as fractals only. Okay? And that concept is used over here to say that, जो पिछले वाला slide था, to say that I will use multiple fins to increase the capacitance. Fractals are one of the most efficient ways to implement very high values of capacitance on chips. Okay? So just looking at this particular device and what it means. So this is the device down there. I hope you're able to see the animation. Over here, I'm talking about the device. And that is the first plate of the capacitor put there, the second plate, and over here you have the bit line there. So again, different kinds of capacitors, planar capacitors, yes. That's the connection. That's like a via. That's the connection that you have from the bottom thing to up there where the capacitor is, nothing else. So multiple different kinds of capacitors have been used, and trench capacitors have been very commonly used. The challenge with trench capacitors is that at that nanoscale, you have to drill a deep trench inside the substrate. You have to actually put an atomic layer of metal, then an atomic layer of dielectric, and then fill the remaining trench with the next metal. And they do that fairly well. They really do that fairly well. But the challenge is, how do you scale this? अब कितना deep जा पाओगे आप? See, when you want to go deeper, if you want to increase the size of your capacitor, you need to go deeper now because the surface area is on the. All of you have looked at the surface area of a cylinder. Maths, class 8, 9, 10th, surface area of a cylinder. That is the area of your capacitor over here. Now, if you want to increase the surface area of your capacitor, what do you need to do? You need to go deeper. Because आप बड़ा नहीं करना चाहते because उससे physical area dimension भी चलेगा. You have to go deeper. Now let me ask you, if I ask you to make a hole which is 1 meter diameter, you can go fairly deep. If I say now this hole has to have a diameter of only 10 centimeters, how deep will you be able to dig the hole? Much lesser, no? Because you don't even have the surface, have the leeway to remove the material from there, is it not? So something similar is happening on the substrate also. You want to scale, reduce the size of the capacitor in that, the diameter of the trench. But then as you reduce that, you want to go deeper also. It's not possible. That is why scaling is an issue. Are you able to visualize this? That as you reduce the cross section of your capacitor up there, you notice that the depth to which I could go reduces. So my capacitance can no longer be as big as I wanted it to be. But I wanted lesser surface, lesser hole size on the top, but deeper. So the technology has to evolve significantly, and that is where there is a limitation to scaling there. Is that okay? So what are the key challenges linked to DRAMs? You want the capacitor to be big. The bigger the capacitor inside the DRAM, the more the charge coupled on the bit line, the faster the bit line will be able to resolve. The sense amplifier will be able to resolve the bit line. Okay? But you do not want the area to increase. So scaling becomes a challenge. A bigger capacitor would also reduce the refresh rate, by the way. So it would make the memory also more available. But area is diamond. And that is where we are pulled in different directions when we are doing DRAM design. We talked about various challenges linked to DRAM capacitors already. And we also already discussed the impact that the size would have on speed and performance. That is speed and area. Performance, so speed is performance, but area. Okay? So we've already discussed this part. And now we go into designing the DRAM array. So in a DRAM, or DRAM totally, in a DRAM, again, just like any other memory, you have an array of memory cells. You also have sense amplifiers, you also have row decoders, you also have muxes. We already said that the word line has to be at a higher voltage level. So you need to have some charge pump inside your post decoder. And you also have other circuits like, and we'll come to those, not designing those circuits, but understanding what are the requirements from those circuits. Those circuits are typically, or may not be custom designed, they may just be synthesized. They are available as an IP there. And IO circuits, for example. All this DDR1, DDR2, DDR3 business, that has nothing to do with the memory cell or anything inside the SRAM and anything inside the DRAM. All that it has to do is with what you do on the outside. Once you get the data, how do you handle it? So these are a part of, so data bus, amplifier, high-speed IO circuits, all these are a part of that ecosystem जो मैं कह रहा था, which is controlled by the coprocessor. Okay. Then you need voltage regulators because you're needing higher voltages, word line voltages, you need charge pumps, you need some voltage regulators around it. And you need repair mechanisms also because DRAMs are far denser than SRAMs. We talked about the repair techniques in SRAMs. Similar repair techniques you will have in DRAMs also. Okay. So this is how a DRAM organization looks like. See, SRAMs we talked about this concept of mux early on. When we started about SRAMs, we said we need a mux. Why do we need a mux? Because we want to play with the aspect ratio of the memory. We want to have more rows, more columns, less columns, depending on my performance requirements, depending on the floor plan of my chip, so many things. I said I want to play with that. In DRAMs, you can't do that. DRAM arrays are always square. Why?
The individual cells are squarish. For address bus.
When I'm saying square over here, I'm saying equal number of rows and equal number of columns.
Because of the memory bus requirements, typically DRAMs will be larger. So, suppose if we have 32 bits of address that is required, so it would be very constrained if we have to keep all the 32 bits in one bus. So, we best case
So,
divided by 2.
DRAMs are your main memories. You want a large main memory. And in this large main memory, there are now many more number of words. Okay, bit width is also large, but many more number of words also. Each word has to be addressed individually. So your address bus is very large. If you try to add that many pins, that's a huge constraint. You only wanted limited number of pins for addressing. So you say that the same address bus you will use for decoding the rows and the columns. If the same address bus is to be used, if it's 10-bit, then it is 1K rows, 1K columns. If it's 20-bit, then the same number of rows and same number of columns anyways. That is why in terms of number of columns and rows, DRAM arrays are always a square. Is that okay? Are you with me? So, देखो अभी क्या होगा in this particular chapter and even in the chapter on flash memories, we'll not go into detail of row decoder design again. We'll not go into detail of sense amplifier design again. We'll now only talk about key differences from SRAMs. Because everything else is, if you understand the SRAM concept well, these differences will take you through. Is that okay? So we're not going to talk about, अच्छा अब इस array के अंदर आप decoding कैसे करोगे? That we've already done. Similar methods will be used here also. Okay. IO side pe mux decoder, tree decoders, all those structures we saw. So similar things will be used here. We'll not go into details of those aspects. We'll only look at where are the key differences from SRAMs. So that if you join a DRAM team, you're not lost. You say, oh, SRAM में तो ऐसा होता है. हाँ, but ये DRAM है. DRAM में ऐसा होता है. Is that okay? So, as I said, same number of address rows and same number of columns. What you need to do is, you need to say that, okay, when I am using the address bus for row addresses, I will give a row address strobe. So that's one signal. That's why I said, I don't know what you mean by the term strobe. For me, the strobe means one strobe that is coming, okay? And when you are sending a column address, you will send a column address strobe. This distinguishes whether the address on the bus has to be used by column decoders or by the row decoders. Is that okay? And then you would organize. So when the rows and columns intersect, that is the cell that you are reading, you would put multiple pages or multiple such arrays into your DRAM. Physically, they are unfolded like this. एक array, दूसरा array, तीसरा array, नीचे एक array, दूसरा array, तीसरा array. Physically, they are unfolded like this. Each such array will store 1 bit of any word. So if you have a 8-bit DRAM, there will be 8 such arrays. If you have a 64-bit DRAM, you will have 64 such arrays. Are you with me on this? So in one array, you are reading only 1 bit. Are you with me? Now, what is the advantage of this? What is the disadvantage of this?
Can't have burst transfers.
Actually, we can have burst transfers. You will just see that. Anyway, एक word read करने के लिए you have to read all the arrays. But I already read them. So actually, burst is an advantage of this. What other advantage of this?
There only a single array, so you can only read 1 bit at a time. So even for the 8-bit, or because we will have larger blocks of data which is we need, so that we don't need to wait 32 times for each of the bits. We can have a parallelism.
So do you remember there was one limitation we said about use of, or one advantage we said about use of muxes. We said in bit scrambling part, we said, okay, अब आपका word 0, 1, 2, 3 एक साथ होगा, bit 0 of word 0, 1, 2, 3 एक साथ होगा, and bit 1 will be 4 bits away. So if a high energy particle comes, soft errors will not happen in the same word. In any given word, only 1 bit will get corrupted. See, DRAM cells are much smaller. So if a high energy particle would come, it can corrupt not just 3 or 4 bits, it can corrupt 20 bits in one go. So if those 20 bits were a part of the same word, there is no way to correct it. In DRAMs, one page has only one bit on it. So if a high energy particle comes, it will corrupt bit number 27 for 20 words. Okay, no problem. But only bit number 27 is corrupted. So when you now need to read from this DRAM, you can very easily correct the error. So ECC is very easy, or just because of this structure, ECC is easy to implement. आपको multiple bit upset का सोचना ही नहीं है. But okay, leakage की वजह से, capacitor की वजह से, anyways, high energy particles छोड़ दो, you anyways need to put ECC inside a DRAM. ठीक है? Now, ECC design for a DRAM has to be done again very intelligently, where you have to take care of a lot of real physical parameters which could happen anytime, and also reasons why things could fail because of, as I just said, high energy particles striking your system. But it's an advantage of this system that soft error rate will be limited, or whatever is the soft error rate, you can recover it easily by the regular ECC that you have in your DRAMs. Are you with me? So now, वो हमने physical देखा था, ये logical है, where we are saying that every page stores only 1 bit. Okay? And every array stores only 1 bit of this. And if you have 8 such arrays, then you have 8 sets of sense amplifiers, 8 sets of everything. And everything gets accessed in parallel. All these pages will get accessed, all these arrays will get accessed in parallel to be able to read the full word. Are you with me? And there's a sequence. Just like for the address bus, we have sharing between row and column. The D and Q bus are also shared. And the control signals are write enable and output enable. When the write enable is on, then it means that the bus is being used for incoming data. When the output enable is on, it means that the bus is being used for outputting, sending data to the processor, to the main chip. Okay. So address or data की 2 buses आएंगी, but there are control signals which will tell which is the direction, like is it to go towards row or column, or whether it is incoming data or data needs to be loaded onto the bus. Is that okay? So let's stop here and we will start with DRAM access and so on in the next class. I again request you, please watch the lecture in advance. All the best.